Hi, my name is Michael Monaghan. The title of my talk is Speeding Up the Polynomial GCD Operation, a Crucial Operation in Maple. The problem is the following. I'm assuming that we're given two polynomials with integer coefficients in many variables, n plus 1 variables here, labeled x0 to xn. And the problem is to compute g, which is the greatest common divisor of the input polynomials a and b. We use this every time in Maple when we simplify a fraction of polynomials. So when you execute the command simplify a over b, Maple computes the GCD g of a and b, and then it divides it out. It divides the numerator by a, the denominator by b, and it returns the simplified fraction. In our work, we're interested in sparse polynomials. We want our algorithm to work well for sparse polynomials. So A, B, and G are sparse. And I'm going to just say what sparse polynomials are. Let di be the degree of g in the ith variable. We say g is sparse if the number of terms in g is much smaller than the maximum number of terms the polynomial could have with degrees di. For example, here's an example of a sparse polynomial. It has 6 variables, x0 to x5, each of degree 4, and it's got 7 terms, 7 non-zero terms. So the number of terms in G is 7. The maximum number of terms is the degree plus 1 to the 6th, which is 15,000. So it has very few terms compared with the maximum possible. And the goal of our work is to get an algorithm for computing the GCD where the cost is polynomial, not just in n and in the number of variables and the degrees, but also in the number of terms. The general approach that we're taking is we're using a modular algorithm. So we compute the GCD of a and b modulo some primes, p1, p2, etc. And then we apply the Chinese remainder theorem to recover the integer coefficients in the GCD. That's very standard. And the difficult part is how to compute the GCD modulo the first prime. That's what we're working on. So what does Maple do? Maple's had a GCD algorithm for a long time, and since 2005, Maple's been using Zippel's algorithm. So I'm just going to describe what Zippel's algorithm is. The input is two polynomials. We've reduced them mod p. We're working mod the first prime. And then we have a loop, and we pick a point from the integers mod p at random. So alpha bar j is a vector of integers mod p chosen at random. And what we're going to do is we're going to evaluate a. We're going to evaluate out all the variables except one at our random point. This is the jth random point. And do the same for b. And this is going to leave us with two polynomials in one variable. And then we compute that GCD using the Euclidean algorithm. So this is an image of our GCD, capital G. And then what we want to do is interpolate. We want to interpolate the GCD that we're trying to compute using these images with the points, the alpha j's, the vectors, alpha j. Let di be the degree of g in xi, and let capital D be the sum of the degrees, and let t be the number of terms in the GCD. Zippel's algorithm uses order dt images, and it solves order d linear systems. So it needs order dt images, and it does order d solves. Several years ago, I and one of my PhD students, Lucas Hu, we developed an algorithm that needs only order t images and does one linear solve. So there's a factor of improvement there of order d. And the idea of the algorithm is to use a Kronecker substitution, and we use a Ben-Or-Tawari sparse interpolation. Before I explain the algorithm, I'd just like to show you the results, how much faster this new algorithm is. So what I've done is I've implemented the new algorithm in Maple with some subroutines coded in C for efficiency. And these are the results that I'm getting on one benchmark. In this benchmark, I'm writing A as the GCD G times A bar. We call that the cofactor. And B is the GCD times B bar. So A bar and B bar are the other factors of A and B. In my benchmarks here, N is 7, so there are 8 variables, and the degree in all the variables is 30. And the polynomials have random 100-bit integer coefficients. And what I'm showing here is the time that Maple takes to compute the GCD of the polynomials, the time of our new algorithm, and we've made a further improvement to the Monaghan-Hu algorithm. So those timings are in this column. And there's 2 blocks of timings here. In the first block, the input polynomials have 10 to the 5th terms. In the second block, they have 10 to the 6th, a million terms. I constructed the input polynomials by creating a GCD with 10 random terms and the cofactors with 10 to the 4th, multiplying G times A bar to get A, and it has 10 to the 5th terms. And I have a set of examples here. So G is small, 100 terms, 1,000 terms. So the size of the GCD is getting bigger as we go down the table, and the size of the cofactors is getting smaller as we go down the table. And what you see over here is how the new GCD compares with Maple. So for this first test, Maple took just over 21 seconds. The new algorithm took 0.66 seconds. And down here, so as the GCD gets bigger, as G gets bigger, it has to do more work because it's got a bigger polynomial to interpolate. So the time goes up. The bottom here, Maple was taking 11,000 seconds and we are taking 45 seconds. So there's a big improvement there. The timings in column N GCD are for the following improvement. Instead of just interpolating G, we are going to try to interpolate the smaller of G and the cofactors. So here, G has got 10 terms. Here, the cofactor's got 100,000 terms. So our algorithm will stop when it finds G. It'll try to interpolate both G and the 2 cofactors, but it'll stop here because G is smaller. Down here at the bottom, it's going to interpolate one of the cofactors, A bar or B bar, and it'll find that instead. So what you see in these timings before, the cost of the GCD problem simply goes up as the size of G increases. Now with this improvement, the cost increases to a maximum and then it drops back down as we start interpolating the smaller of the cofactors. So in this test right here, where I was able to compute the GCD in Maple, 11,000 seconds, by computing this cofactor instead, I'm able to do the computation, the GCD computation in 1.4 seconds. So it's roughly a factor of almost 10,000 improvement. I'd like to explain 2 things. One is how the Ben-Or-Tawari sparse polynomial interpolation works and what we needed to do to modify it to work well for the GCD problem. So the Ben-Or-Tawari interpolation goes as follows. Let's suppose we have a polynomial C that we're trying to interpolate. Let it have T terms there, and with coefficients AI, integer coefficients, and monomials MI. The context in the GCD problem, C would be one of the coefficients of G that we're trying to interpolate. Ben-Or and Tawari, they assume that you're given a term bound, capital T, on little t, the number of terms of C. In practice, we won't know or won't have such a term bound, so one needs to modify this algorithm in order to also determine what little t is. Again, little t is the number of terms in C. So the algorithm goes as follows. we compute some evaluations. We evaluate our polynomial C at powers of primes. 2 to the j, 3 to the j, 5 to the j, etc. Pn is the nth prime, Pn to the j. And we do this for 2 t points. The algorithm needs 2 t points to interpolate the polynomial. Let little mi be the monomial evaluation, that is mi evaluated at the primes. If you have two monomials and you evaluate them at primes, you're guaranteed to get distinct integer evaluations. Let lambda of z be the polynomial whose roots are the monomial evaluations. Then the second step of the algorithm is to compute t, to figure out what little t is and what lambda of z is. Using those evaluations, we use the Berlekamp-Massey algorithm from coding theory to do this. The next step is to factor that lambda polynomial. That gives us the monomial evaluations. Then we factor those integers. It's not hard because they have small prime factors. We use trial division by our primes, and that will give us the monomial. For example, if one of the integer evaluations, the monomial evaluations, is 45,000, factor that integer, you get 2 cubed, 3 squared, 5 to the 4th. That immediately tells you what the monomial is. It's x1 cubed, x2 squared, x3 to the 4th. You just read it off. And the final step, so at this point, we will know what the unknown monomials in the polynomial are. The final step is to solve for the coefficients of the polynomial. It's a linear system. It turns out to be a shifted van der Waals system. And we're solving, V here is a van der Waals matrix. We're solving VA equals B, where Vij, the ijth entry of the van der Waals matrix is mi to the j. We know those mi's at this point. That's the algorithm. However, there's a major problem with it. Those integers bj, that we get when we evaluate the polynomial at powers of primes, since j can be big, j goes up to 2t, these can be massive integers, huge integers, and that ruins the efficiency of the algorithm. But there is a simple solution, principle, and that is to compute modulo a prime. We are going to execute the Berlekamp-Massey algorithm, the Benoit-Tawari algorithm modulo a prime, because we're doing the GCD modulo a prime. So one does steps 1, 2, 3, and 5 modulo a prime. And how big does the prime need to be? It needs to be bigger than any of the monomial evaluations. Here's a bound that will work. When you do that for n equals 8 and degrees 10, I get that the prime would need to be bigger than this 69, almost 70-digit integer. So yes, it's not huge, but it's still very big. And a 69-digit prime would mean that we can't use the machine. Our machines, our computers do 64-bit integer arithmetic. So this prime would overflow the machine arithmetic. So that's a problem. So what we did in our algorithm is we did the following. We use an invertible Kronecker substitution. So the Kronecker substitution is going to take a polynomial in n variables and map it into a polynomial in one variable. Here is the Kronecker substitution. We replace the first variable by y, a new variable, the second by a power of y, the third by a larger power of y, etc. How big do the powers need to be? In order to invert this mapping, we need that the RIs are bigger than the degrees, the DIs. This gives us a univariate polynomial whose coefficients are AI and exponents are EI, say. And this is what we're trying to interpolate. We're trying to find now the coefficients as before, but now it's a polynomial in one variable and we're trying to find those exponents. They can be larger, of course. The algorithm goes as follows. We pick a random generator alpha from the integers mod p. Our points are now the Kronecker mapping of C evaluated at powers of alpha to the j. same range. This time, mi will be alpha to the ei, and we let lambda of z have roots mi as before. We use the Berlekamp-Massey algorithm again to determine t and lambda of z, and then we factor lambda of z to get the roots using Cantor-Zassenhaus, using the Cantor-Zassenhaus algorithm. Now, in order that the roots are distinct, we need that the prime is bigger than the mi's, alpha to the ei. Once we've done that, we are trying to get the exponents. We have to solve this equation in the integers mod p for ei. That turns out to be a discrete logarithm. It's possible to do that if our prime is what's called a smooth prime. In our GCD application, we're free to choose the prime, so we're going to be forced now to choose p to be a smooth prime. But there are lots of smooth primes, so this is not a serious problem. Then we proceed as before to solve the van der Waals system to get the coefficients. And how does this work out? For the same prime, for the same experiment as before, where we had 8 variables and all of the degrees of the variables were 10, the size of the prime works out to be, it needs to be bigger than 11 to the 8th, which is a much smaller size. And I've just got a little note down here that our actual codes, it's using 62-bit primes. And this is the first prime that it tries. It's a 62-bit prime. It's a smooth prime. Factorization of p is 61 times 67 times 2 to the 50 plus 1. So that's what we do. I have some further notes about the implementation. We've coded, as I mentioned in the introduction, the implementation is in Maple with some subroutines coded in C to speed up the implementation. So these are the parts of the code that we've implemented in C. I've implemented it in C. And in this table, the complexities of my implementation are shown on the right. I had to code evaluation of the polynomials at alpha to the j in C. I coded the Euclidean algorithm in C. I coded the Berlekamp-Massey algorithm in C. I coded the root finding algorithm in C. That's the Cantor-Zassenhaus algorithm. We need to compute discrete logs. I coded this in C. This is not the bottleneck of the algorithm. Maple has a discrete log implementation, which would be fine. But I coded it in C. And I also coded the van der Waals solver. I'm using Zippel's order t-squared van der Waals solver. And of these complexities here on the right, D is the sum of the degrees of the GCD. And this first term is the evaluations are usually the most expensive part of the whole algorithm. And that's because of this factor here. What's S? S is the number of terms in A and B. It's the size of the input. It's the number of terms in the input polynomials. We have to evaluate those polynomials at each point. There are order t points, and each one costs order s. So that's usually the most expensive part of the algorithm. So if we want to speed this up, I need to look at how to do the evaluations faster. Thank you for listening. I have a table of references if you're interested in looking up the papers.